Hi, now the second lecture. The topic here is solving systems of linear equations. So let us consider a system of m linear equations in n variables x1, x2, xn. So this system has been displayed in its full glory in this slide. The first equation is a11 x1 plus a12 x2 plus dot 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 plus a1n xn equal to b1. A21 x1 plus A22 x2 plus dot 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 plus A2n xn equal to B2 dot 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 etc. AM1, the last equation is AM1 x1 plus AM2 x2 plus dot 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 AMN xn equal to BM. Now this equation can be written in matrix form as AX equal to B, where A is the coefficient matrix AJK. The AJK is the matrix A of these coefficients AJK is called the associated matrix. And you got this column vector B1, B2, Bm. This is a column vector, the unknown. This is also something that is given to you, part of the equation. And so now what you do is that you take this associated matrix. A is called the associated matrix. To this associated matrix, what is the size of the associated matrix again? It's an m cross n matrix. There are m rows and n columns. So what we do is that we augment to this associated matrix this last column consisting of the right hand sides b1, b2, bm. And we form this new matrix A plus, A superscript plus, which is A, the original matrix A. You simply throw in this extra column B. This is called the augmented matrix. So now, if you give the system of equations, you can surely read off from the system of equation what the associated matrix is, and you can also read off what the augmented matrix is. So basically, there is no need to keep writing this x1, x2, xn. You can simply reduce the piece of writing just by displaying this matrix, the augmented matrix. The augmented matrix contains all the information that you need about the system of linear system of equations. So the idea is, what is a systematic procedure for solving this system of linear equations? Before we get down to the theory behind it, the basic algorithm is called the Gauss elimination method, GEM, Gauss elimination method. So the Gauss elimination method is described in the next few slides. But before we get to the Gauss elimination method, let us look at a simple example. Let me just display a handwritten slide. So the Gauss elimination method, let us explain the method through a simple system of three equations and three unknowns. I deliberately chosen a simple system so that the algorithm becomes very clear. We are not lost in a morass of complicated expressions. So we got three equations: x plus y minus 2z equal to 4, 2x minus y plus z equal to minus 1, x plus 2y minus z equal to 3. We got these three equations. And so what is the associated matrix? 1, 1, minus 2, 1, 1, minus 2, 2, minus 1, 1, 2, minus 1, 1, 1, 2, minus 1, 1, 2, minus 1. Go to the right hand side, the column vector 4, minus 1, 3. So you augment. So the associated matrix is the one that has been indicated in this red circle, in this red curve, inside the red curve, and I marked it as associated matrix. And I'm augmenting it by throwing in this extra column 4, minus 1, 3, 4, minus 1, 3. And this entire 3 by 4 matrix is called the augmented matrix. So what would you do? The obvious idea is eliminate x between the first two equations, correct? If you eliminate x between the first two equations, you get one equation in y and z. Then you will eliminate x between the first equation and the third equation, and you'll get one more equation in y and z. So all in all, you will get two equations in y and z which you will somehow solve, and then you will first find your y and the z, and then you will find your x. That's the procedure. So how do you eliminate x between the first and the second equation? Subtract from the second equation twice the first equation. Subtract from the second equation twice the first equation. What is going to happen? The first equation, I'm not going to touch it. It's going to be as it is. So subtract from the second equation, right? So this x will be gone, and you'll get minus 3y. You'll get minus 3y, right? And then you're subtracting from the second equation twice the first equation. So you're going to get 5z. You're going to get 5z. And then you get minus 4, minus 8, you're going to get minus 9. So the second equation, there's not going to be there is going to be no x in the second equation. So the new system, the new system becomes this. The first and the third equation are intact. The second equation has become slightly simpler in that it doesn't involve the x variable. So let us write the associated matrix and the augmented matrix for the transformed system. Now you will agree with me that instead of solving the original equation, it is enough to solve the transformed equation, this new equation. This new system and the old system are completely equivalent. From the first system of equations, you can come to the second system of equations. Conversely, from the second system of equations, you can pass on to the first system of equations. So the set of solutions for this system is identical to the set of solutions for the second equation. But the second system has an advantage that one of the equations doesn't involve an x. But now this process of subtracting from the second equation twice the first equation. So let us observe what we are doing. We're going to subtract from 2 times the first equation. But now instead of keeping the x, y, and the z in the game, let us remove the x, y, and z, and let us remove these plus signs also, and let us remove the equality signs, and let us just stare at the augmented matrix. Isn't performing this the same as saying R2 prime equal to R2 minus 2R1? From the second row, subtract twice the first row. From the second row, subtract twice the first row, and the new row that you obtain, it will be called R2 prime. R2 prime is the new second row. The new second row is the original second row minus twice the first row. And if you do that, you get a 0 here, you get a minus 3 here, you get a 5 here, and you get a minus 9 here. That's exactly what is going to happen. So there's no need to work with the system of equations with x, y, z, with all these plus signs, with all the equality signs. We simply write down the matrix. And the idea of eliminating x means that this 2 should be removed and it should become a 0. And the way to make the 2 into a 0 is subtract from the second row twice the first row. Now we want to eliminate. The next step is to eliminate x between the first equation and the third equation. You subtract from the third equation the first equation. Subtract from the third equation the first equation. But that is equivalent to saying R3 prime equal to R3 minus R1. Isn't that so? This procedure is exactly the same as saying that there's no need to work with this x's, y, all this x, y, z, and all the equality signs, etc. We can suppress all of them. Just start with this augmented matrix and simply say R3 prime equal to subtract from the third row the first row, and the new third row is called R3 prime. R3 prime equal to R3 minus R1. That gives you 1, 1, minus 2, 4, 0, minus 3, 5, minus 9. And the last row has become 0, 1, 1, minus 1. So now you see that in this new system of equations, there is no x in the last 2 equations. Now I have got 2 equations. Now let us momentarily ignore the first equation and let us manipulate the second equation and the third equation. Now it is very tempting to add to the second equation 3 times the third equation. If I add to the second equation 3 times the third equation, the y will disappear from the second equation. And the y will disappear. So that is equivalent to saying that I will somehow try to make this minus 3 into a 1. I must get rid of this minus 3 and make a 0 in the 2, 2 position. But I can do it in 2 ways. I can do it in two ways. I can add to the second row 3 times the first row, or I could add to the second row 3 times the third row. Which one of these options is superior? Let us see. Suppose I take the first option. Suppose I add to the second row 3 times the first row. You surely get a 0 here, but you are tampered the 0 here. The 0 which was very desirable here has now been tampered, and that will become a 2, that will become a 3. So that's not a good idea. Whereas if you do it the other way around, if you use the third equation and add to the second row 3 times the third row, then what happens? You do get the 0 here, and this 0 that you already originally, we did a lot of work to get the 0 here, and that work remains intact. The result of that remains intact, so you get 0. So this original 0 that we obtained in the 1 position remains 0. So now this is a superior way of doing it. So it is 1 1 1 1 minus 2 4, 0 0 8 minus 12, 0 1 1 minus 1. So now from the second equation, you see the second equation simply reads 8z equal to minus 12 and z equal to minus 1/3. So you got z equal to minus 1/3. The third equation now says that from third equation you can get y, and once you get your y and the z, you can substitute and you can get x from the first equation. So that is how the systematic elimination of the variables. But instead of eliminating the variables, we work with the augmented matrix and we perform row operations. These operations, R2 prime equal to R2 minus 2 R1, R3 prime equal to R3 minus R1, and then multiplying the second equation by 8. That is multiplying the second row, multiplying the second equation by 1 by 8, excuse me, multiplying the second equation by 1 by 8, or multiplying the second row by 1 by 8, or R2 prime equal to 1 by 8 R2. That is another row. These are called elementary row operations. These are called elementary row operations. You might want to exchange, you might want to write the third equation, second equation last, and you want to write the third equation second. In other words, you may want to switch the order of these equations. That is equivalent to switching the two rows. So that is also, so there are 3 types of elementary row operations. Adding to a given row a multiple of another row. For example, R2 prime equal to R2 minus 2 R1. Multiplying a given row by a non-zero number. Non-zero. 1 by 8 is a non-zero number, and multiplying the second row by 1 by 8. The third kind of operation is exchanging two rows for convenience. I mean, interchanging the positions of two of the equations. Writing the second equation third and the third equation as second, for example. That is exchanging R2. So that I will write it as R1 two-sided arrow. I'll write R2 two-sided arrow R3. That's how I'll say that R2 and R3 are being exchanged, row exchanges. So these are the 3 elementary row operations, and this procedure, this technique of systematically doing this. So why should we do this? How do we go about this? So you see the pattern. There is a 1, and we got this. We try to get these zeros below, and then what will happen is that I will switch these two rows. I will write this third row. It's the second row as the third, and third row will become the second, and I will get this 1 here, and below the 1 I'll get the 0 here. Okay, and so there's a terminology behind all these things, and this terminology is now explained in the next few slides. So let us now go to the slides and see what the slides are saying. So in order to solve the system of equations, Gauss proposed 3 kinds of operations, each of which gives a new system which is completely equal to the original one. Interchanging two equations, right? Writing the second equation third and the third equation second. That is obviously a valid operation. Multiplying an equation by some non-zero number, or multiplying an equation, adding to an equation a multiple of another equation. R2 prime equal to R2 minus 2 R1, for example. Adding to the second row, adding to the second equation minus 2 times the first equation. So these are all, each time you perform this, you get an equivalent operation. And instead of performing it on a system of equations, you simply perform these operations not on the system of equations. There's no point in writing all those x1, x2, x3, all the plus signs and all the equality signs. You can skip, you can suppress all these symbols, and you can just work with the augmented matrix A plus. So there are three elementary row operations. The elementary row operations are of these three kinds. Okay, so now I'm going to tell you another thing, that these operations are denoted by these symbols PJK. PJK means interchanging the jth and the kth rows. Operationally, I will be writing RJ double-headed arrow RK. EJKC, adding to the kth row, adding to the jth row, C times the kth row, or multiplying a certain row by non-zeros. You might be asking, why am I using this symbol PJK, EJKC, and MJ? There is a reason for that. There is a reason for that. So any matrix, so these are called the elementary row operations. Elementary row. So what is a row echelon form? The row echelon form is basically what I just, this is an example of a row echelon form. So you started out with a you started out with some 4x4 matrix, for example, or 4x7 matrix. It doesn't have to be a square matrix. Okay. So what did we do? Suppose, for example, all the rows and all the entries in the first column is 0. Suppose all the entries in the first column is 0. Ignore the first column and move on to the second column. Okay. Now let us assume, on the other hand, that at least one of the entries in the first column is not 0. Maybe the third entry was not 0, right? In the original matrix, by the way. In the original matrix, the coefficient in the augmented matrix, it happened that, say, the third entry, this entry, the 3-1 entry happens to be non-zero. Then what you do is you choose whichever is non-zero, you choose that, and you switch those equations, switch those two rows. There is switching two rows if necessary. I may assume that the 1-1 entry is non-zero. This will happen if at least one entry is non-zero in the first column. If all the entries are 0, then we move on to stage 2. Straight away skip step 1 and go to step 2. Okay. Now assume that at least one of them is non-zero. But by switching rows, I can assume that the 1-1 entry is non-zero. If the 1-1 entry is non-zero, suppose the 1-1 entry is, say, 6. Then what do? I will subtract from the second row some multiple of the first row and make that 0. Suppose the second row is, suppose this entry is, 1 and this entry is 6. Then what will I do? R2 prime equal to R2 minus 1 by 6 R1. If this number is, 8, and if the first number is 6, R3 prime equal to 8 upon R3 prime equal to R3 minus 8 upon 6 R1. So use an appropriate multiple, subtract or add a multiple of the first row, Rj prime equal to Rj plus some multiple of R1. So by doing that, I can make all these things 0. Or case 2, all the entries were 0 to begin with, in which case you simply go on to the second column. So now do the same thing in the second column. Now that you got this beautiful pattern, don't disturb these zeros. These zeros are going to remain for the rest of the discussion. In other words, row 1 cannot be used anymore to perform. Only thing you can do with row 1 is, if this coefficient is not 1, I can divide by that coefficient and make this coefficient 1. That is the only possible thing. Beyond that, I can't do anything else. These zeros are not to be disturbed. So go to the second column. Go to the second column. Ignore this and then so now ignore the first row, and repeat ignore the first row and the first column, and repeat whatever we did with this with the remaining with the smaller matrix. Okay, so it turns out that if you do that, perhaps here is an example where you got 3 0 0 0 as a first column. The second column you got 2 1 0 0. You got a nice you got this pattern of zeros below. You are not to use row 1. Row 1 is out of the game. So now you have to ignore this row 1 and you have to repeat the whole process with the smaller matrix. And then the first column is not to be touched. There are zeros here. And then you must simplify the remaining smaller matrix. And then, okay, so you did that and you got a 1 here. We are very happy. It's 1 0 0. Now that you got a 1 0, these zeros are not to be touched. These zeros are not to be touched. These zeros are not to be touched. If these zeros are not to be touched, row 1 cannot be used, row 2 cannot be used anymore. So row 1 and row 2 are gone. Now look at the smaller matrix. Oh, in the smaller matrix, both these are zeros. Skip, therefore go to the next step. Go to the next step. And then start with the next one. Okay, so now these rows cannot be now these rows cannot be used because you got these two are zeros, and then go to the next one, and you get this number. Now this 12 is the fourth position. Switch it, bring it to the third. Switch the last two rows. And make this row bring the 12 in the third, in the 3-4 position, and 0 in the 4-4 position. So now you got this pattern, non-zero, and then below that 0. Once you got non-zero and below that 0, then the first row is gone from reckoning. The first column is gone from the reckoning. Then see if all of them are 0, then move on to the next step. And then look at what is happening here. If all of them are 0, go to the next one. So now in this particular example, you got this 1 here and you got the zeros below them. Okay, now this row cannot be used anymore, and these zeros are not to be touched. Because if you try to use this row to do something else, then you can use this row to make this 2 as 0, but that is not required. That is not necessary. We are only interested in the below the equations below this. So don't use this row to tamper these zeros anymore. These zeros are not to be tampered, not to be touched. And then go to the next one. So these numbers, and then there is one more step to be done. The last two equations should be exchanged so that the last row is 0 0 0 0. And these numbers that you get 3, 1, and 12 are called the pivots. They are called the pivots. The columns in which the pivots occur are called the pivotal columns. The columns in which the pivots occurs will be called the pivotal columns. The other columns will be called the non-pivotal columns. So which are the pivotal columns? Column 1, column 2, and column 4 are the pivotal columns. Which is a non-pivotal column? The non-pivotal column is the third column. The third column is a non-pivotal column. Okay. So now what you do is the following. This is called the row echelon form. This is called the row echelon form. Now what is a reduced row echelon form? The reduced echelon form is such that I can multiply. Remember I told you there's one more operation I can perform on the first row, namely make this number 3 into a 1. Multiply the first row by 1/3. They are allowed. And multiply this row by 12 and make it 1. Ideally, you should be switching. This 12 should appear as a third row. So the third row and the fourth row should be switched, and 0 0 0 1. You can make that. And so you can multiply this row by 1/3 and make this pivot 1. And you can multiply this by 1/12 and make this pivot 1. So when the pivots are all actually 1, then you call it a row reduced echelon form or a reduced row echelon form. Reduced row echelon forms is mainly for theoretical interest only. We are not going to make any use of this reduced row echelon form. We are going to work with row echelon forms only. So here is an example. Okay, so here is an example. 3, 2, 1, 3. The augmented matrix is given. Okay, so what you do, you perform the elementary row operations. So multiply the third row, subtract from the third row twice the first row. Subtract from the third row twice the first row. So this will become a 0, for example. So that's how you have to keep systematically doing that. And you perform a row operation on this, and you get your row echelon form. This is the row echelon form of the matrix. It is not row reduced, because to get a row reduced echelon form, you have to multiply the first row by 1/3 and to multiply the third row by 1/12. Okay, so now you saw that every time you perform a row operation, you get a new system which is equivalent to the original system. So this original system is equivalent to this new system. What is the new system? 3x1 plus 2x2 plus x3 equal to 3. x2 minus x3 equal to 6. That's the second equation. The third equation is 0x1 plus 0x2 plus 0x3 equal to 12. What does that tell you? This tells you that the third equation, that this system cannot have any solution. This system cannot, this transformed system, the row reduced system cannot have any solutions. Therefore, the original system cannot also have any solution. Okay, so this is how you can read off. The advantage is that after you systematically perform a row operation, when you systematically perform row operations, you are able to get a much simpler system from which you can read off whether or not the system has a solution. Here you see another example of a similar kind. You got a system of 4 equations in 3 unknowns. 4 equations in 3 unknowns, and the row operations have been performed, and the last equation simply drops out. 0x1 plus 0x2 plus 0x3 equal to 0. So that's a tautological statement. You can just forget about it. And effectively, you got 3 equations. And the first equation reads minus x1 minus x2 plus x3 equal to 0. The second equation reads 10x2 plus 25x3 equal to 90. The last equation reads minus 95x3 equal to minus 190. So the last equation will immediately give you x3. Once you get x3, then you can go back and find x2. And once you get x1 and x3 and x2, you can go back and find x1. This is called back substitution. So you can get back substitution and you can find x1, x2, and x3. So here in the next slide, you see systematically how the row operations are being performed. Okay, so it is basically R2 prime equal to R2 plus R1. The new second row is the original second row plus R1. So that's how you got this. That's how the second row becomes 0, 0, 0, 0. So that is the way the. So here are some more equations, and so we will stop here. Lecture 1B. Thank you.